So we're going to start by finding the area of a circle. And the area of a circle is just pi r squared. And the idea here is we want to find area and polar. And polar is all based around circles more than anything else. And the problem is when you have a polar coordinate, you have some sort of radius and you have some sort of angle. You don't have the full circle, you just have a slice of it. I mean, you might have the entire circle, but you have to write this area as a function of theta. Now, the common thing about this is theta equals 2 pi to go all the way around the circle. So I can't really just say it's theta r squared. I mean, the 2 is there. So the formula, which is actually, this is called a sector, is we're going to take not pi over 2, theta over 2 r squared. That's the area of the sector. And the idea of turning this into a calculus-based idea is we're going to take our little slices, and our slices in this case are going to be little sectors. So they're going to be, you've got this arc going on here, and each slice is going to be kind of a rectangle. So a little piece of pie, if you may, for each of them. And the width of this theta would just be d theta. So area and polar coordinates is going to be r squared d theta over 2. And then you're going to just take this from A to B. And that's really it for your area and polar coordinates as far as the formula goes. Now, a couple things that are going to be kind of interesting is, especially when you start having numbers in front of theta, it really messes with your period, and you don't always know what that's going to look like. And unless you're really familiar with polar graphing, you're going to have to rely a little bit heavier on the calculator, or you're going to have to do a lot of work just to envision what the area is going to look like on a polar graph. Now, one of the things we are going to want to do is, if we can, we're going to graph them on the calculator. If you can't graph them on the calculator, if you're not quite used to that yet, we can plot points, and some of these you're going to start to know. But if we have one petal of the rose curve formed by this. So a lot of times we're going to start by graphing on the calculator and seeing what in the world they mean by one petal in the first place. So we'll bring the calculator up. And in our y equals, we're going to write 4 sine of 4 theta. If you looked at that last one, we had a cosine function. Now think about the window that we need. Sine of theta ranges from -1 to +1. 4 means that my window should go from -4 to +4. And I'm just make this go to 2 pi. I'm not going to want to run around a whole bunch of different times. -4 to +4. Keep the scale what it normally is. -4 to +4, and we should have a good window. So we see our rose petal going around here. And that keeps going. We want the entire thing. We could take one of these and then multiply it by 1, 2, 3, 4, 8. So if you wanted 2 petals, you could find the area under 1 and double it, or you could keep going. Now, a couple things you want to check out here. If you hit the trace button, as it traces to the right here, it doesn't necessarily always go in nice increments. Now this is right back really close to 0. It's not quite at theta equals 0.77. And you also notice as I'm going to the right, the little cursor's moving to the left, and that's dealing with having a negative radius. So even though theta hasn't even reached pi over 2, we're over here in the third quadrant. So you can't really just expect that when it hits, that it's going to go here, at pi over 4, and then over here pi over 2. It doesn't really work like that. So as you follow this around, to find where the petals can come back here to start, so start at 0 here, and back over here wasn't pi over 2. So to find that, all I need is to know when the radius is equal to 0. So the first time and the second time the radius equals 0, that's going to be my first loop. So over here, we're going to set our radius equal to 0. So 0 equals sine of 4 theta. Well, sine of theta is equal to 0 when the inside, in this case 4 theta, equals 0, pi, and normally just 2 pi, but we saw that was a lot more times than just that. So the way to get this is we divide by 4 to everything. So theta is going to be 0 like we knew. And the next one is going to be pi over 4 and pi over 2, etc., etc., etc. And that's why you get so many different loops. Now, I could really care less about the rest of these because we just want 1 pellet. And even if we wanted all of them, we could take our 1 pellet and multiply it by 8. So for here, it's 1/2, 0 to pi over 4. And we're just going to write it in our R for sine. Now, if I was going to do this myself, this is what I would really do and put it on the main screen. If you're going to do this in the y equals, you don't have the new operating system, you're really going to want to go back to rectangular. So we go to rectangular coordinates to be able to find the area of the curve. If you go and look in your calculator, and normally you would say, okay, let's find the area of the curve, second calc, 80. Doesn't give me the option. It'll allow me to find the slope at a given point. So if you wanted to verify that it was a horizontal tangent line, you could use your slope here. And it gives you d r d theta, change in r or change in theta. You don't use that one very often, but it doesn't give you an idea for area in the curve. So to actually do it, I would quit myself, hit alpha window, and go down to number 4. And then proceed to do your integral just like so. I'll let you do that one on your own. Alright, now this next question is a tricky one. And it really kind of requires you to either know what these graphs look like or use a graph. So let's bring up a graphing calculator. And in our R equals, really, put both of our equations. 3. And go to the graph. Okay, well, here comes the first one. Alright, here comes the second one. So when we want to know the common interior, you're looking here, the first graph had, all of this was the first graph's interior, and all of this is the second graph's interior. So we're looking for one of these regions. Well, actually, we're looking for both of these regions. Now, to do that, we can use a lot of symmetry if we'd like to. So symmetry that we can use is, well, I can take this piece and double it to find the whole thing, or in this case I could take this half and now bring it up the top half and quadruple it. Now a couple things you got to be careful about on here. When you trace your first function, I would always do this. I would press trace and then trace it out. It doesn't start here. It starts up here. This is 0. If I arrow to the other function, R2, and I type in 0, see where that starts at? Second function starts here, and it goes up. So I really want to use my second function from 0 till, well, it might be easy to tell. And you can do a little bit of guess and check just to see where this is going to be. And it looks like theta is right here. No, I pressed up instead left. So you might think pi over 2. Well, let's see what happens. Second, pi over 2. Yep. I'm going backwards. So it goes from 0 to pi over 2. And that kind of makes sense to be over here at 0, and as it goes up around, it gets to pi over 2. Now you really only like loop into other quadrants when it's not just theta. If it was 4 theta, you might have a much better chance of getting into a different quadrant. If you remember, that really stretches or shrinks your period on a sine graph. Okay, so what I'm going to do is I'm going to use R2, not R1, from 0 to pi over 2, and then we multiply it by 4. So 4 integral, and remember it's theta. And you have a r squared. So we have 3, 1 minus sine of theta squared. So that's my formula, and I'm going from 0 to pi over 2. So as far as arc length goes in polar, we have a pretty easy formula. I mean, it's not easy looking, but it's easy to come by. So in parametric, we have arc length to be this. Basically, you change an x squared, change a y squared, and it's usually dt, but t is just some sort of variable. And in that case, you can think of these as being parametric more than polar. So you can do a lot of your polar in parametric. But x equals r cosine theta, so dx d theta squared, you have to go back to this. dy d theta squared, you have to go back to this. So the arc length formula, I again would not memorize this, just like the derivative formula I wouldn't memorize. I would memorize the process and do it individually on each problem. So we need dx d theta, so r prime cosine theta plus r sine theta. Sorry, actually minus, because the derivative of cosine is negative sine. So that's my dx d theta. We square it. The square root of the whole thing. Plus, and now we got to do our dy d theta. So r prime sine theta plus r cosine theta. All this squared. Do an integral. And really just d theta at the end from a to b, where a and b have to be values of theta. So this formula is really, really long. However, you want to remember that x equals r cosine theta, y equals r sine theta is the same like cosine and sine that you have on the unit circle. If you think about this, the unit circle, the radius is 1. So if you're having trouble remembering that, x is cosine from the unit circle and y is sine from the unit circle. We just have to toss the r in front because we're not doing a unit circle. We're doing a circle of radius r. So to actually find the arc length, you need to find x, dx d theta. So x equals r, so 8, 1 plus cosine theta, sine theta. And then you also need y, which is r cosine theta. So 8, it might actually be easier to do 8 cosine theta, just distributed it in there, times cosine of theta. There's our x, there's our y, and over here again it would be like 8 plus 8 sine theta plus 8 sine cosine theta. And over here you'd have 8 cosine theta plus 8 cosine squared theta. So we've got both our x and y, and we want the integral from 0 to 2 pi, square root of, and then there's just the distance formula, change in x, dx dt squared, change in y, dy dt squared. So the problem is you end up with a lot of product rules, you end up with a lot of big formulas, but the good news is you're not doing much of this by hand. So we got 8 cosine theta, and then over here you got to do a product rule. Plus 8 cosine squared theta minus 8 sine squared theta. So that's my dx squared. And unfortunately, we got to do the exact same thing for our dy squared. Plus negative 8 sine theta. And then drop down your 2. It's going to be a minus here in a second. So the 2 comes down with the 8 up front. 16 cosine of theta times the derivative of the inside, which would be the sine theta. I've already taken care of the negative. Close this off, square it up, d theta. Now, you can clean this up a little bit if you'd like to. There's not much you can do inside each of these. You can square and then combine like terms. There'll be some things that combine, some things that won't. And in the end, you're really just going to dump this in your calculator. So be very careful when you type in the calculator. Make sure you put some parentheses around here, raise it to the power. People forget the powers every once in a while, which I think is one of the easier things to remember, but they get forgotten. So the arc length of these, it's tedious, right now dx and dy, but it's pretty easy.